You may be familiar with quantum physics through some of its famous experiments, like the double slit experiment or the EPR experiment, or Schrodinger's famous thought experiment with a cat that's both dead and alive. This makes quantum mechanics sound very strange, and it is. But it's also important to keep in mind that all physics, aside from relativity, is quantum physics. It's just that the strange parts of quantum mechanics sort of wash out for most intents and purposes. But consider the double slit experiment. Imagine firing particles at a barrier with two slits in it. In a classical setup, a screen behind the barrier would show two bands where particles would hit after passing through one slit or the other. When done with small particles, however, such as photons, we see something very different. An interference pattern emerges, as though it were not particles but waves traveling through the two slits. Somehow, this happens even if photons are emitted and sent through the experiment one at a time. The motion of small particles seems clearly wave-like, and yet when emitted and detected, we seem to be working with particles. This was a profound crisis for scientists, and it's at the heart of quantum mechanics. It has led many to advocate for a wave-centric, if not wave-only, view of physics. And yet it seems impossible to ignore the particle side of things. This has led, for many years, to the prevailing notion of wave-particle duality. And yet it's hard to make sense of this idea exactly. Particles become waves and then become particles again when observed. This line of thinking has led to a great deal of spilt ink and consternation, although eventually, seemingly, acceptance. And yet there is a far simpler ontology possible. Particles could always be particles, and especially very small particles may be influenced by some kind of wave. This would explain the wave-like trajectories we see, as well as the particle behavior. Also, there's no question of wave function collapse, which is necessary in other interpretations to explain how the sort of spread out probability distribution of the wave function results in simply a single particle at a single position when we do the experiment. For a good and thorough introduction to this model, called the pilot wave model or Bohmian mechanics, I highly recommend the Stanford Encyclopedia of Philosophy entry under that title, Bohmian Mechanics.